Just wanted to remind you that Friday we're having a joint lecture, so Professor Jarbo will be subbing for me on Friday. My wife is having a minor surgery, so I'm going to be the good husband and take her to the hospital. So that's 1414 Molly Bio. I think you should be familiar with that lecture hall, right? So just remember that. I think it's in the Canvas calendar, so I think Slack will remind you too, but lots of reminders is better than not enough. Speaking of reminders, again, the pretest 2 is due tomorrow. Let's make sure you get that in there. Homework coming in on Friday, so remember to bring that with you, and you can just give it to Professor Jarbo. Any other questions before we start today? Okay, so let's get started then. Okay, so there are a few things that I want to cover today. All right, I just kind of talked in general terms about entropy on Monday. Today, I want to get a little bit more specific, talk generally about heat engines, and today that's going to lead directly into the Carnot cycle. And so the Carnot cycle is an imaginary heat engine that happens to operate completely reversibly, so that means there's no entropy generated, and that therefore represents a thermodynamic limit as to how much work you can get out of a given amount of heat. And so even though it's fictitious and imaginary, it's an incredibly useful thought experiment because you can use Carnot analysis to apply that to real processes and see how efficient they're operating. And you can also use it to challenge wild, fabulous claims of new processes that claim amazing things. You can apply Carnot analysis to those to see if they're realistic or not. So that's the first item, and then we'll have a brief aside. In order to do any calculations that involve entropy, we need to be able to calculate state changes in entropy, and with state changes, ideal gases are the easiest places to start. And then, as I've mentioned before, even though ideal gases are also fictitious, they remain useful in real calculations because the ideal gas state is an imaginary state that we can use real equations of state to transform real gases into conceptual ideal gases. So ideal gas equations are useful even when you're dealing with real gases. And then we'll start to talk about process analysis, where you're using entropy calculations. And so somewhat analogous to an energy balance, we're going to have an entropy balance, with the main difference being entropy is not conserved. In the ideal world, you can have conservation of entropy, and that's a reversible process. So it's only conserved for a reversible process, and that's where delta S is going to be 0. Okay, so let's start with the heat engines in the Carnot cycle. So the last thing that I did on Monday was start to argue why heat can only go from hot to cold. So the picture that we have is we've got a hot source and a cold sink. and you've got some heat that's leaving the hot reservoir. It's going into some process, and then it exits to the cold reservoir. So if we start with one of the expressions of the second law, that says that changes in entropy are equated to a reversible heat flow divided by the thermodynamic temperature. And so if all this process is doing is transferring heat, so there's no work involved, then the delta S for that process with respect to the process is going to be minus QC times TH minus TC over TC. Okay, when we go through these analyses, the signs are going to drive you bonkers. They drive me bonkers, and I guarantee I'll get it wrong at least once unless I'm in truly good form, and I don't think I've had enough coffee yet this morning to guarantee perfect performance with respect to signs. Okay, so the heats that I'm going to be using, this is defined with respect to the process. So given that is QC positive or negative? I know it's hard to talk, but you can raise your hand. Positive or negative with respect to the process? I want you to talk about it for 30 seconds, and then I'll take the poll one last time. And I want big, exuberant hand raises this time. Okay, with respect to the process, is QC positive? Raise your hands. QC negative? Raise your hand. Perfect. The arrow is going away from the process. That means heat is leaving the process, which means it's negative. All right, perfect. So with respect to the cold reservoir, then it is going to be positive, right? So negative QC is greater than 0. All right, and this is a good thing because the second law says the delta S has to be greater than 0 for a real process, or it can be equal to 0 for an imaginary reversible process. Okay, so written this way, this is greater than or equal to 0 if and only if TH is greater than TC. Yes? It's the same thing, it's just a different algebraic expression. And on Monday, I didn't include the process, so my sign convention for Q's was different. And this is the same thing the book does. And if you read the beginning of chapter 5, I'm kind of tracing through that derivation for you. Okay? Okay, so first, that says that entropy can only increase if the hot is actually hot. All right, and so that's why heat flows from hot to cold. The second part of that is the only time we get to delta S equals 0 is when TH equals TC. All right, and looking at the math, that's kind of a, well, of course it is. That's obvious. But conceptually, it's an important observation because heat transfer is only reversible when there's no temperature gradient. So there is no heat transfer if it's reversible. Like, there is no such thing as reversible heat transfer. It exists completely as a figment of our imagination, which kind of makes this numerator part look a little fishy, huh? If heat transfer is never reversible, then how do you imagine it being reversible? Well, it's the isothermal process that we've been pretending is reversible. Remember, we're Q equals minus W. That is a fictitious process that is reversible, where there is heat transfer, but it is only fictitious. So you have to imagine calculus style that there's a differential heat transfer, so that given an infinite amount of time, you can transfer heat from a hot body that's only differentially hotter than a cold body. Okay? Practically speaking, turns out that if you have a process that's pure heat transfer, then you can drop the rev subscripts on that equation. All right, so with processes where it's heat transfer only, or if you're just focused on a heat transfer only subset of a process, the entropy flow for that process is just going to be the heat transfer divided by the temperature at which the body is either delivering or receiving the heat. Okay. All right. So that's basic heat transfer. All right. So now let's look at this again. Except now let's not constrain ourselves to a process that doesn't generate any work. All right, I want to be able to draw on you again. Perfect. All right, so we're going to take another copy of this diagram here. And so now the work doesn't necessarily have to be equal to 0. Okay, sign conventions again. Is work positive or negative? It's negative. It's going out of the engine. So with respect to the engine, QH is greater than 0, QC is less than 0, and W is less than 0. Now, previous editions of the text, when they went through this derivation, as an effort to make keeping track of all the signs easier, they used the absolute value bars on the heat symbols, and that's also something that I did slightly differently on Monday. I kind of like it that way because it helps me focus on the math and not trying to keep track of what's positive or negative. But it's also you can make arguments that it's better without the absolute value signs because it makes the statements of the energy balances, for example, less prone to making mistakes as well. So let's look at this process then. We're going to use both first and second law now to get to the equations that we want. All right, so this thing, we're going to call this a heat engine. And like the engine in your car, heat engines operate in cycles. So they go through a series of steps, and the state of the engine is exactly the same after one complete cycle, and it's ready to. So every time it goes through a cycle, it's going to consume some heat, it's going to produce some work, and it's going to eject some heat. So over one full cycle is what we're going to do an energy balance on. So the change in internal energy for engine for one cycle, and it's a lot of decorative superscripts and subscripts, and I'm not going to write them every time, but I just want you to have that in your mind, that's what we're talking about here. So I'm just going to say delta U for that. but we're talking about the engine. We're talking about one complete cycle of the engine. Because it's a complete cycle, the state is the same at the beginning and the end of the cycle. So there's no change in internal energy. And likewise, the overall change in entropy for the engine, both delta U and delta S are going to be equal to 0. Okay, and so for the energy part, delta U is going to be equal to the work produced by the engine, and remember that's less than 0, and then the total amount of heat injected into the engine. So that's going to be plus QH plus QC, where remembering that QH is greater than 0 and QC is less than 0. Because the sum of those things has to be equal to 0, we can immediately conclude that the work produced by the engine is just the sum of the negative of the sum of the heats consumed by the engine. So the difference between the amount of heat going in and the amount of heat going out. All right, so far so good? All right, so this part, that's just for the engine. So if you want to do a second law analysis, we have to do a tallying of the entropy effect on the universe, not just the engine. So here the universe includes the hot reservoir and the cold reservoir. So the delta S total, so the delta S of the universe, that's going to be the delta S for the hot reservoir, the delta S for the cold reservoir, plus the delta S for the engine. And we've already agreed, I think, that that's got to be 0 because it's a cyclic process. All right, so the delta S then is going to be, for the hot reservoir, we're going to go back up here, and we're going to remember that changes in entropy are equal to heat flows divided by temperatures. And here is a place where you got to be careful with signs. I wrote the symbols QH and QC with respect to the process, which means they are backwards with respect to the surroundings. So the amount of heat flow with respect to the hot reservoir is not plus QH, it's minus QH, because the arrow is pointed in the wrong direction with respect to the reservoir. Okay, that's a subtle point, and this is one of the easier spots to lose track of the signs. And then the temperature over which that transfer happens is TH, of course. And then likewise for the cold reservoir, positive QC, even though QC is less than 0, plus QC is with respect to the heat engine. So if we're doing an entropy tally, that's going to be minus QC over TC. And that's delta S total right there. All right, and remember second law says that this better be greater than 0, or if we've got our thought experiment hats on, then we can allow it to be equal to 0 for a perfect process. So let's look at each term and make sure it makes sense. So QH is greater than 0. We acknowledge that. So negative QH is less than 0. So this contribution to the overall entropy change of the universe is less than 0. Okay, so this is, the universe doesn't like that. So this part had better be positive then, or else we made a mistake. So QC, this part is less than 0 algebraically. So negative QC is positive, and thermodynamic temperatures are always positive. So that part is less than 0, and that's good. All right, so we're in good shape. All right, so now the next step to get to a useful conclusion is we're going to take the first law and we're going to combine it with the second law. So just a little bit of algebra here. So I'm going to multiply both sides of the second law equation by TH. So I'm going to have TH delta S, and I'm going to drop the total subscript. I just want you to remember that it's there now. We're still talking about the total entropy. That's going to be minus QH minus QC over TC. All right. To combine those two equations, it would be great if I had a minus QH minus QC in this equation. So I'm going to add and subtract QC. Yeah.
Shouldn't, if you're multiplying nothing by TH, shouldn't QC times TH?
Thank you. Yes.
So if QH is with respect to the reservoir, is QC with respect to that system?
Both are with everything is with respect to the system, which is why I have a negative sign in front of the QH and a negative sign in front of the QC. If these heat flows with respect to the reservoirs, they both have positive signs. So if QH is with respect to the reservoir, then the reservoir is ejecting heat. And so QH algebraically would be negative. Okay. If QC with respect to the cold reservoir, it's accepting heat. And so the algebraic sign of QC would be positive. The overall entropy effect on the universe, though, is when you lose heat, you're losing entropy. When you get heat, you're getting entropy. So the hot reservoir, however I've defined my conventions here, it better be negative, less than 0 for entropy change. The cold reservoir that's accepting the heat is increasing the entropy. All right, so the next step is just a little bit of regrouping then. So we're going to take minus QH, and I'm going to move this minus QC over, and then the QC with the temperatures is going to factor with the QC that I had to add to keep the math straight. So we're going to have a plus QC, and then we're going to have 1, and that's from this one, and then we're going to have minus TH over TC from the other one. Yes?
Yeah,
Pardon?
where is the QC from?
So I want to combine first law and second law together. So I want my entropy expression to have a minus QH minus QC in it, because then I'm just going to substitute work. So I started with my second law equation. Then this is a multiply by TH, and then I'm going to add and subtract QC. So I didn't change the equation. I added QC right here, and I subtracted QC right there. and now I'm just regrouping.
You adding in the first law.
I haven't substituted the first law yet. That's going to be the next thing that I do. So now to get the first law in there, we note that this is W by my first law equation. So that means that the TH delta S is work plus QC times 1 minus TH over TC. And if I want to rearrange this for work, which I do, we're going to say work equals TH delta S minus QC times 1 minus TH over TC. So now that we're here, so the first observation is that this is the work produced by an ideal heat engine when delta S is equal to 0. And for a real heat engine, delta S is going to be greater than 0. So there's a couple limits of interest. So the first is, so what happens if there is no work? So if there is no work, then this just reduces down to a simple heat transfer that we started with. So if there's no work produced, W equals 0, and we end up with delta S equals minus QC over TH times 1 minus TH over TC. No, I don't want that minus there. So this one is just a rearrangement of this one. Maybe it'd help if I numbered my equations. So equation 2 is just a rearrangement of equation 1. And if we go back up here, this is the same as equation 2. So if work is equal to, so a heat engine that produces no work is just describing a heat transfer from a hot to a cold body. Okay, and then equation 3 then, this is going to be Carnot's equation. So if delta S equals 0, the heat engine is ideal. And so it is called a Carnot cycle in honor of the inventor of these equations. Carnot was a French engineer. So if we take the delta S out of equation 1, then we simply get W equals minus QC times 1 minus TH over TC. I believe the book prints this equation with the subtrahends reversed, which changes the sign, so that's the same thing. And another rearrangement that you'll see published will be TH over TC minus 1, or the minus 1 can also appear in the numerator as TH minus TC. And so these are all collectively called Carnot equations. So another thing that we can do is go back up to first law. So let's call this one equation 5. So I can make a first law substitution again. So that's first law from above. And so what that substitution looks like is minus QH minus QC, plugging in for the work term. For that piece of it right there. And so that's TH over TC minus 1. You doing all right? Good? All right, so we get to another Carnot equation pretty quickly here. So I'm just going to split the fraction up on the left. So I'm going to have minus QH over QC minus 1 equals TH over TC minus 1. And I've got minus 1s on both sides that can be eliminated. And we get to yet another Carnot equation. All right, and that one's also pretty useful. And there are a few others. There's one more incarnation in the book that's pretty easy to get to. They're all interchangeable though. So if you were to remember 2 of them, I would remember equation 4 and equation 7. And there is another one in the book, which is W over QH equals TC over TH minus 1. I don't want to spend too much time on algebra. Yeah. So this is where I am in the book. All right, so all these equations allow us to manipulate relationships between the temperatures of the reservoirs, the heat flows that are going into and out of the reservoirs, and then the ideal amount of work that any process that converts heat into work is going to be able to achieve. And so what we're interested in is how much work, that's the valuable product, do we get for the price? And that's where we start to talk about efficiencies. And so the first efficiency that we define in the course is the thermal efficiency. And in words, this is simply what we want over what it costs. So QH comes from the combustion of fuel or whatever, and the electricity or the motivating power that drives your automobile or the product, the work product of a turbine is what we're paying that cost for. So for a heat engine, the thermal efficiency is going to be the ratio of what we want over the cost. And because we've defined W with respect to the engine, W is negative and we like our efficiencies to be positive. So we got to put that negative sign back in there. So just as a quick example we'll get to in a second here. And so eta is the symbol we use for efficiencies in the course. And so this is this expression, we'll call it equation 9. So that's going to be the Carnot efficiency, and it's going to be the maximum that you can get. So Q over WH. Sorry, one more step. We'll do equation 10 will be the Carnot efficiency. So equation 9, this is a generic definition of efficiency, and then the equation 8 version, we have a substitution for W over QH that puts things in terms of temperatures. And so what happens now is the thermal efficiency for an ideal cycle is just going to be 1 minus TC over TH, where the ordering of the subtrahends again flipped because of the minus sign. All right, and so that says that you can only perfectly convert heat into work if your cold reservoir is at 0 degrees Kelvin. All right, so that is the limit that allows you to have perfect thermal efficiency. So, or the hotter the source of QH, the more efficient the process is. So if you were able to generate steam by directly boiling it using the sun, so that'd be a pretty long pipe. But if you could do that, then your TH would be huge, and you would have nearly perfect thermal efficiency, even if you were dumping it into a river at 300 Kelvin. Okay, but there are practical limits to what we can use for TC and TH, right? So we don't have a lot of thermal reservoirs laying around that are much better than 300 Kelvin. You can generate cooling water at a plant that's maybe 275 Kelvin. But it doesn't naturally exist at that temperature unless you're in the Arctic Circle. So if you want colder than 298, you're going to have to pay for it using a refrigeration cycle, and then you're just kind of shooting yourself in the foot. So cooling towers, you'll see them outside the cogen facility. Those are your QC reservoirs right there. You're working at basically atmospheric temperature for your TC. For your TH, if you're boiling if you're burning natural gas, you can get flue temperatures, easily around 800 to 1,000 K. Those solar concentrators that I was talking about, and you're also generating recirculating fluids that have really high temperatures like that. So the quality of your heat is directly related to its temperature. So you want hot, and very cold, and you get better thermal efficiency. So just as a kind of a typical example, if you want to see what a regular power plant might be operating at. So suppose we have a power plant that's generating 800,000 kilowatts. It uses steam. And that's going to be at 585 Kelvin. And it's dumping waste heat into a river at TC equals 295 Kelvin. And the plant is not a Carnot plant, it's a real plant. So it's going to operate at a fraction of ideality. So some of the best turbines in the world can approach 80% efficiency, which is actually not too bad. More realistic value might be 70%. So what we want to know then is we're just given those efficiencies. What are QH and QC? So we'll start out by calculating the Carnot efficiency. So eta Carnot is going to be 1 minus 295 Kelvin over 595 Kelvin. So the Carnot efficiency for this process is only about 50%. So the 70% sounds pretty good until you're like, oof. The perfect heat engine here is going to be wasting half of what it burns. So half of a perfect process's fuel consumption just goes to satisfying the second law. All right, so once we've got that, then we need to find out what the actual efficiency of the process is. So the thermal efficiency is, remember, minus work over QH. And so that's going to be 70% of the Carnot efficiency. So that's going to work out to be about 35%. Or if you work it out to more digits than we need, we get 34.65% real process efficiency. And then to solve for QH, then it's a simple multiplication there. So QH is going to be roughly 3 times the amount of work, and I don't have the actual number written down, so I'm not going to take the time to write it because I'm running short on that. I will write the equation down. So QH is going to be minus W. So the W is 800,000 kilowatts divided by 0.3465, and that is going to be roughly 2.35 megawatts. So my in-head estimate there is just basically multiplying that by 3 and then shaving off a little bit because I'm not dividing by a third. I'm dividing by a number slightly bigger than a third. I do have a number for QC written down though, so we'll go all the way there on that one. So QC plus QH plus W equals 0, right? So QC is going to be negative 800,000 kilowatts, because QH is therefore going to be minus QC minus W. All right. So looking at that, do you agree with the sign that I put on the 800,000 kilowatts? Yeah? Yeah, work is leaving my process. I define W with respect to the process. So W is less than 0. And my energy balance says I need a negative sign in front of it. So there it is. I promised I would make at least one sign mistake before the day was done. So QH is equal to negative minus 800,000 kilowatts. That is minus W. All right, how about QH? Is QH the right sign? Yeah? Yeah. And that is just a typo. Pardon? Yeah, so I got the sign right on the right-hand side, but just because I made 2 sign mistakes, right? Too wrong to make it right every now and then. All right, thank you for keeping me honest there. So we'll call that 13. And that one 14. So even in these simple problems, you can make some simple mistakes that can be hard to hunt down if you're not careful. So now we're going to do minus QC. I wanted to solve for QC, didn't I? QC is minus W minus QH. All right, so QH is positive, so this is going to be a simple negative number. All right, and so now if we work it out to the full number of digits, we're going to get to 1.51000 kilowatts. And this is what goes to the river. All right, so 1 kilowatt is enough to raise 1 kilogram per second of water by 1 degree Celsius. So and this is gigawatts, not megawatts. So I have 1.5 billion joules per second of energy that's going into that river. And so you can guarantee that unless it's a huge river, you are actually going to be raising the temperature of the river when you do this. And that's where thermal pollution comes from. So that algae blooms and things like that. It's a realistic amount of power for a power plant to generate. Okay, that is a good stopping point for today. I will see you on Monday. Professor Jarbo will see you on Friday.